Good morning. This is the calc project for William Kendrick, Phil Johansson, Christian Bladen, and John Musciano. So in our project we tried to design a hourglass, and here is our makeshift hourglass. And the measurements that we took from this makeshift hourglass are here. The diameter of the middle, which is the little part where in between the two nozzles of the bottles, is 2.5. The total length is from end to end is 23.3 centimeters. The big diameter, which is from here to here, is 10.8 centimeters. And the length of the curve, which we consider the curve to be from about the red line on the Coke bottle to the edge, the final end. And each of those, which is their two, to be 9.9 centimeters. And then the length of the middle is approximately 3.1 centimeters.
So, from the measurements that Musciano just described in the part 1 of this video, we were able to discern these 4 essential points to creating this graph right here, which is a representation of our hourglass on a XY plane. So the values on this graph are point A, which is right here, is negative 11.5 and 5.4. So it's 5.4 up and negative 11.5 over. And point B, which is this, which is going to be the end of the curve and the start of the flat part, so the middle of the section right here, is negative 1.53 and 1.25. So it's up 1.25 and over negative 1.53 to get to there. And the way that we got these points was we went over the measurements. And the first value that we have, the length of A, which is negative 11.5 over, so absolute value 1.5 over from there, is half of the total length of the thing, because it's half of this. The graph splits this down the middle. So half of 23.3 is just about 11.5. So that's how we got the distance to this point. The way that we got 5.4 is half of the diameter. If going through the center of this is going to be a line, and we're going to take the radius to figure out how high up it is. We know the diameter of the big part, which is 10.8. Half of that is the radius. So we come back over here. Half of 10.8 is 5.4. The radius from here to here. It's very similar for point B, which is the start of the flat part. So 1.53 is the absolute value. And we get that by taking the length of the middle, which is how far over it's going to be left and right. Half of that is how far it's going to be over left and right. And so we divide that by 2 to get 1.53. Well, 1.55, but we had to change the measurement. And then to get 1.25, we come back over here, and the diameter of the middle is 2.5. So to find the radius, we just divide that by 2, and that is how high up we're going to go. So that is how we figured out point A and B. And then from there, you just reverse the sign on the x values of it, and then that lets you flip the points over onto the other side of the y-axis. From there, you connect the points using a cosine graph to measure the curve that we're using. So this to here is a cosine graph. That's a straight line, and then this is the other half of the cosine graph. And that is how we came up with the measurements and how we decided on what to use as a graph. So from our decision to use a cosine graph and a straight line, and using these points right here, we were able to create this graph right here, and through the math, we were able to create these 3 graphs right there, these 3 functions, which all fit into one graph as in the f of x function. That's why we're able to do this entire line singularly throughout the entire interval of it without there being any chopping up of the points, or they're not being discontinuous. So the way that we got these graphs right here, these 2 graphs are essentially the same thing. The way that we got the different phase shifts and amplitudes and yada 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 for the graph is first we come over here, and the most essential part of it is finding the amplitude. So the amplitude, the way you find amplitude is you take the radius of one and take the radius of the other. So the radius of the big part of the graph and you subtract the radius of the small part of the graph to figure out how high, like the distance from the trough to the peak of the cosine wave. So that's how you get the distance. Now to find, because when you take a cosine wave, you split it down the middle, the amplitude is only half of the distance from the trough to the peak, you divide it once again by 2, and that's how you get the amplitude. So using 10.8 is the big diameter, divide that by 2 for the radius, right there. 2.5, which is the diameter of the small curve, divide that by 2 for radius, you get 1.25. Divide that all out again, you get 2.075. You come back right over here and you put that out front because this is the space for the amplitude on the graph. Next, for the vertical shift, you come over here and you know that you've got to shift the entire graph up by the distance of its amplitude so that at the very least it is going to always, the integral of it is always going to be positive. That way the very bottom of the trough is not going to be negative. From there you shift it up an extra 1.25 because that is half the diameter of the middle. So if the line is coming straight through the middle of this hourglass, you want it so that this part, the very bottom of this, is 1.25 up. So to do that, you've got to move it up 1.25, but also move the cosine waves of it up the distance of the amplitude.
So we also needed to incorporate horizontal shifts to allow this straight section of the graph at point C and point B between those 2 points. And we were able to figure this horizontal shift by doing 1/2 the wavelength minus 1.53, which is the distance that we want to be shifted on either side. And that equals 8.4, and from this 8.4 we divided it by the 1.53, again the total amount that we want it to be shifted, and then we took that answer and divided it by the amplitude, and that gives us 2.6. And this 2.6 is what is found in the equation that allows both cosine graphs to have minimum points at B and C. So lastly, to find wavelength, it's just simply 2 pi over what you want the wavelength to be. And what we want the wavelength to be is 9.9 times 2, because 9.9 is the length of half of the curve. So we do 2 pi divided by 2 times the length of the curve, 9.9, which simplifies to pi over length of the curve, and that will give you wavelength, and the wavelength turns out to be 0.315. So after all that we found from vertical shift, amplitude, horizontal shift, and wavelength, we can, and plugging that back into the cosine function, we are given this function and this piecewise function, and the x values for this piecewise function simulate the intervals from a to b, b to c, and c to d.
So we have our function here again that we saw earlier, and our graph of the function right here. And we want to find the volume of it. So what we're going to do is we're going to make the function simulate the radius of these two parts. So this part will be the small part right here, and these two will be the larger parts. And so we're going to rotate around the x-axis to find the volume. And to do that, we need to integrate. So we use pi r squared to find the area, and we integrate it because that'll give us the volume.
Okay, so once we found our integral equation, which is right here, we need to plug in our functions, but since it's a piecewise function, you need to do it separately, 3 times separately for the specified coordinates. And once you plug in the function 3 times, you do evaluate it from negative 11.5 to 11.5, and when you bring it all together, you get the number right here. And we wanted to calculate our percent error, so we did the whole equation and we found out that it's 23.3%.